Is it getting audio and everything? Okay. So we're gonna, I guess, as the semester goes on, people start getting here a little bit after and after, but we'll try to make an effort to start it at 1:30 most days. I'm not giving a lecture today, but I have a few announcements to make. The first one is that I did send out some emails today regarding people who are on the roster, but not on Piazza or vice versa. If you are in that boat, please respond to me or somehow else. And if you're here especially, please let me know what the situation is. The flip side of that is for those on the wait list that there's plenty of room in the course once we make all these things clearing out. Well, not plenty, but there is room in the course once we clear everything out, so there will not be an issue. It will go through by the end of this week or next week at the earliest, or at the latest rather. So don't worry if you're on the wait list. If you are on the wait list, want to be in the course, you will get in the course. So you don't have to worry about that at all. And I think with that, the other things were the lectures on the lecture page on the website. There's also now a tentative schedule listed as a spreadsheet, which can be a little bit easier than going to the syllabus, and plus we can make changes more easily and kind of update the syllabus. So you can refer to that for what lectures will be coming up. And then there was one comment on the Piazza about us suggesting additional material. We're happy to do that. At least for most of my lectures so far, it was not intended for you to read anything beforehand. I'm happy to point to additional material on that. But do you have anything different about that?
For the search lectures, the initial search lectures, there's nothing extra.
Okay.
But as we go on and we get into more specialized fields, there'll be additional readings of the paper to describe additional.
Yeah, we can link to them on the lectures page as well. So we'll post that. And then the other thing, and even for the lectures starting next week, I'm going to be starting lectures on numerical optimization, and those do not have a chapter in the textbook. So for that, I will post additional material as well. But turn it over to you. Oh yeah, there was a question back there. Oh right, yes. Okay, finally, last thing. I knew I was forgetting something. We have a room for TA office hours, both Tuesdays and Thursdays now. Finally, I'm going to say it wrong if I say it right now. So how about I will just, even during class, I will run up and get my laptop and post it on the website. In Tuesdays, it's in Wien, and on Thursdays, it's in Gates somewhere. I'm not quite sure where, but somewhere. And I will post that during class, so you will, starting tomorrow, be able to come to office hours at a set time every week for the TA office hours. Our office hours remain the same. It's just after class, walk with us back to our office and stay there for an hour. How do you do this? I put it in my pocket and clip it on somewhere. Pretty good mic.
All right, so first of all, I want to apologize for the fact that I have no voice right now. It seems like it always coincides right when I have to teach. So it's an unfortunate aspect of this thing. So if you can't understand me, just remind me to speak up. I don't know why. It always seems to happen right now. So today we're going to talk about search problems and search procedures. As Zico has said earlier, there are multiple definitions and a variety of definitions that you might apply to artificial intelligence. But the one that we're sort of focusing on is optimization, and in particular, more on practical approaches to very complex problems. So the idea is that when I'm teaching you search here, I'm going to be showing you solutions to how do you address problems that are exponential in space, exponential in time to find. And you're trying to find ways that you can find decent solutions that are practical given this very expansive space. What I'm not going to be talking about, as Zico also pointed out, is I'm not going to be talking about cognitive architectures, semantics about these meanings, these kind of things. So this search is going to be talking about very real-world problems that you might want to address this way. So given that, by the way, this is in response to one of the requests during the class, and so here are the readings for the search lectures. Note that the search lectures are actually going to be interrupted due to my schedule, so we're going to go into the discrete state search, which is what I'm doing, and then Zico is going to do constraint, numerical optimization, and then I am going to go back and revisit some of the search lectures. So sorry for that interruption, it's just due to the schedules. So today's lectures, we're going to talk about why is problem solving a key technique in AI? Where does it show up? Why are you going to use it? And then we're going to go through sort of the basic strategies for how you formulate and solve search problems. I know that I often, almost in everything I do and almost all the projects I address, the first thing I do is I think, I don't know how to solve this problem. All right, so what am I going to think about? What are all the possible states I have to think about that might be a solution? And then what are the initial states? And then what are the types of things that I can do to transform that initial state into the goal states I want? So we'll go into how to do that, but when I talk about this, this is something I do in my life every day. Even when it comes to like, how do I get my kids and get my homework and get those things done and get my lectures ready, you know, all those kinds of things, I still do that way, all right? And then finally is, we're going to talk about some of the blind or uninformed search strategies that are, you may even be familiar with them, but I'm going to review them just to make sure that everybody's on the same page. And if we have additional time, I will go into some of the parts of the informed and heuristic stuff, just depending on how the lecture progresses. So the first thing I wanted to do is just motivate why you might want to do search, why search is really important. So one of the things that's really easy for me to do is because I do, like I said, I do it in every part of my day. So here I just picked I threw a net over the projects that I'm doing actively now. There's even some additional ones. Few of you actually will recognize some. So this would be like a Boeing project. So you'd recognize it, and you'd recognize it. And here what we have is this notion of a manufacturing floor. And we have a bunch of robots that are taking parts to an assembly station, and they're putting them together. There are requirements in this world. And these requirements in this world are things like, we don't want to get too many parts at the assembly station in advance of that, because then there'll be a lot of congestion, there won't be room for the parts. Parts will be all hanging around the space. There are humans, so you don't want to run into that. And you want to basically be able to deliver those parts just in time, and then get out of there and allocate the appropriate robots that have the capabilities to carry those parts to those assembly stations. So in order to do that, you know, we can go into details much later, but not right now. In order to do that, you have to be able to understand the constraints on the robots, how you're going to do the allocation on the robots, what path they're going to take to get from the parts place to the assembly station. And those all represent constraints on both the bindings for the locations and for the bindings for what can carry the parts. And in order to figure out all the different possible robot combinations that could carry the parts at that time to get there to meet those constraints, you're essentially going to use search to explore all those varied different combinations. Similarly, here is another project that I'm actually working on. And what's interesting about this project is now what I was talking about here was done all in a centralized reasoner. So you have a reasoner that can just sit there and look at the entire world and think, here are the constraints there, here are the constraints in the assembly station, I know all about the robots, I have complete world information, and I can have complete control about when those robots are allocated. All right, so that becomes really, you know, that's advantageous, obviously, because then you don't have to deal with a distributed problem of information being across a network. But it's not realistic in many environments. So a different kind of search is one that requires a distributed search. And in this, what this problem is, just very loosely again, is this idea that you have people out in the world, in this case it was military, but it could also be commercial, using their cell phones. And if people wanted to be able to take advantage of the empty cycles on those cell phones in order to monitor and assess the band usage in that particular area, so who's doing what at certain frequencies, what channels, you'd like to be able to do that. And of course, the moment that you want to use your phone, then that transmitter's got to be reallocated back to your phone. It can't be working on that other kind of concept. So, but the difference here is that nobody has complete information about the whole world and where everybody is. It's requests come into it, just imagine from some, you know, foreign place, and they come into a system and you don't know where they are. So if they came in, and this is the point, as you noticed probably if you're familiar with Pittsburgh yet, and there's a bunch of cell phones out there, they have to figure out how are they going to allocate, what cell phones are going to be allocated to satisfy this request, to find out in this location how the band usage is being done. And in order to do that, go ahead. Question? Okay. So if in order to do that, what they would have to do is they would have to coordinate among themselves. And that's by sharing information. In this particular case, they're doing something that was called a contract net protocol, which is essentially the idea of I ask everybody what they're doing. Everybody tells me, oh, I can do that request. And they give me back something. And then I go ahead and then I use some kind of protocol for making a decision about how to allocate that. So again, what happens here is when I'm making a decision about how to allocate those radios, I'm using search. I'm taking the information about when you're available and when you're available and when you're available and what part of the problem you can do and what space you can do, and I'm merging them together to find out what's the minimum set coverage that I can get to cover that space in the time that was required to do those requests. So this is done in a distributed sense. It has partial centralization once it collects those bids, but it's done in a different model than the centralized one. Here's just a notion of something that's just actually applied and working out in the world. I don't know if you guys have ever seen those access vans out there, out in the streets, and probably been stuck behind them when they're stopping and the blinkers are on. They're out there to pick up the disabled and the elderly. And they are a perfect implementation of a problem known as the vehicle routing problem with time windows. And they're basically pick up and drop off problems. And so what you do with this thing is that you have a problem here where you go out and you pick up and you have a bunch of vehicles and you're trying to assign those vehicles and those to make itineraries for those vehicles in order to pick up all the requests that are asked for. And what makes it a little bit more complicated is that in itself is a static problem, which is great, and this is something to understand, is that these problems are, if you knew all the orders, all the requests in the beginning of the day, and you say, go ahead and schedule them all right, then you're just in the static problem of trying to order them on the vehicles that you have, and usually you're going to try to optimize something. So in one of the cases here is you try to minimize the distance they travel in order to save on gas, in order to save on time, and also to meet all the hard constraints about when you promise that you're going to pick up these people. So what makes this problem a little bit different than these two, it's a little bit more like this, is that this has to be done during execution. Orders come in all the time as you're scheduling. People cancel their request, and so at that point you have to be able to constantly readjust the scheduling. Again, what you have is you have these timelines that are out there. You have these pickups and drop-offs on those timelines for these vehicles that are out there. And then what you're going to do is you're going to, when something cancels, you're going to make space. You have to pull them out and make space. When something gets inserted, you're going to try to find on all the possible vehicles out there, what's the best time to insert that vehicle on there so that I can meet that and still maximize sort of the flexibility while minimizing the distance that I'm adding to the overall problem. So again, search is done here. This is a very kind of a near back to the distributed world, but it's something that you guys can all relate to. Here, if you guys ever been out to East Liberty where the Target is and all that area out there. So the lab I work in, we run all the signal traffic lights out there. And so we run all the traffic lights and also now send down Penn, and pretty soon we're going to be doing, over the next couple of years, a whole corridor that goes up from East Liberty, from Wilkinsburg up on Penn, all the way up over Baum into the city. So it'll be an alternative corridor to 376 to get into the city. Yeah?
Two questions. Are you optimizing for the network? And are you doing adaptive control, or are you predicting the flow of data?
Right. So we are doing adaptive control based on predictive flow. All right. So what I mean, not sure everybody is as familiar. You seem somewhat familiar with this. So the idea here is that you have advanced sensing, and so we have advanced sensing on our segments basically, and there is a coordination that goes on across where you're sending information about what your expected flows are, meaning that what cars are coming from that intersection, they're going to go to the next intersection. Go ahead.
Are you optimizing all the network? Taking into account all the loads being driven?
Right, so it's not quite like that. It's hard to do that because of all the side streets and all the where we're specialized is not arterial flows. Arterial flows are basically big, long flows that don't have lots of ingrounds and things. But there are a lot of ingresses and egresses from the network that are not censored. They have no sensors, no detection, no lights. So it's very hard to do it from a complete holistic point of view here. So what we do have is actually a much more local strategy for doing this. I'm not going to go into great detail, sorry for the digression. But the idea here is that you can see flows coming and you're trying to, you lump them in together or in things that are called platoons, and then you're trying to optimize when those platoons are going. The only power that you have at these lights is either to extend the phase or to shorten a phase, meaning make the green longer, make the green shorter. And that's the only power you have. It's the only effector you have to do this. And the way you use this search is that you figure out when things are coming and you're deciding about when to extend and when not to extend. There is some coordinated, it's more sophisticated than that, but all I wanted to get across was this, is that the idea is that we have very local, each one of these lights has their own search engine, their own scheduler engine, and they do that based on information that they gather from their neighbors. So again, it's a small-scale search problem for each one of them. The harder problem is pushing information. But again, without search, we wouldn't have a solution here. And finally, just really briefly on this one, this is purely military. And what is that you have currently in the military right now, you have stovepiping. People that do air planning do air planning. People that do cyber planning do cyber planning. People that do ISR, which is the reconnaissance and surveillance, they do that planning. And then at some level, they talk to each other to coordinate their missions. And what they want, what the military would like now, is a more integrated system that can play trade-offs. So if I have to take out a target, if there's more than one way, if I can use an air attack on that target or an electronic attack on that target, you know, you'd like to be able to do those trade-offs in a holistic way. And in order to do all those trade-offs among space and air and risk and factors and deployment and, you know, using it and how many times you can use it and all those kind of resources, you have lots of different variables that have to be assigned values. And again, to do that kind of planning is fundamental to that is search. So here are just, and this is just my little small window of, you know, of the world. And yet all these projects all are fundamentally search projects. So hopefully you can see that there is a realistic reason why you're going to need search if you're going to attack problems that are complicated. There are no closed form solutions to any of these problems. There's too much uncertainty, too much complexity. So you have to understand that you're going to need to be able to formulate these things. All right, that took entirely too long, but we'll see what goes on now. So here, let's go down. Now that I've gone from these vast, big problems, let's go to the toy problems so that we can better explain the algorithms. So here are some simple kind of search problems. Games are always great ways to search problems because they have very discrete states. Excuse me. So one of the easy ones is this ape puzzle. There are different types of goal states you might have. You might want to have them in order. This would be a goal state. This would be an initial state. And the question is, what kind of, how would you use search to transform this using legal moves into that goal state? All right. Similarly, there's you can do this in these crypto-arithmetic problems where you have something like this. This is a really classic problem. You've probably all seen this one, in fact, where you have send more money, and you say, well, this is supposed to add up to this. How do you assign values to the letters in order that it will actually add up? And if you look at it, these are the this is the solution. I'll let you guys look it out to see, make sure that it works later. Okay, another really popular problem you see in AI research that uses it as a base case for almost everything is this notion of an n-queen problem. And the idea of the n-queen problem is you set up a board of n width and n height, and then you put that many queens on it such that none of the queens can attack each other. All right, so this is a classic problem. One of the reasons that it's kind of a neat problem is you can imagine in a search engine, you're going to look and try to enumerate all the possible states and then rule out states or not generate states that are going to actually be in violation until you find a possible state. And note, one of the things about this is that this is strictly, the way I framed it, is a satisfaction problem. It's not an optimization problem. You're finding some state in the board that will satisfy the constraint that they can't attack each other. We're not saying one configuration would be better than another. Okay, so this is just to show you, after a lot of work, there's actually a closed form solution to this problem for n to whatever. And so what makes it interesting about this, though, is that this kind of gives you a kind of lower bound on what you might be able to find at, and if you use it as search, you can see how far off you are. So just again, really quickly, there are lots of instances where you'll see search, you'll see insignia interpretation, theorem proven, where you do substitutions of different kinds of values in order to do on the axioms. Combinatorial optimization, any kind of layout you do. For example, I had a project where I was doing layout of welding, and you're trying to minimize the number of setups so that you don't have to keep moving the parts around. And in order to do that, you would have to do some kind of optimization of how that would lay down, what's the best way to lay them out in order to minimize those setups. Robot navigation, Zico gave some examples of that. It gets more complicated. Certainly we have some of that robot navigation in freeform in that Boeing, or the robotic project I had, which was the top one to the left. Also, there's ones that are graph-based, which is the one that Zico showed, and I'll give you another example of that later. Factory scheduling, as you can imagine, I've already showed you a bunch of scheduling applications. This is a big-time one for me, and again, this is something that showed up in that one that was in the upper left-hand corner. Symbolic computation, and a billion other ones. So it's a critical one to know. All right, so how do we formulate search problems? There are states and state spaces. You're looking at anytime you start with an initial state, like we saw that the 8 puzzle, it was in some initial state, and as we go to transform it, we can transform it in a number of different ways. All the different ways we can get it will be all those states. In order to transform it, we have to know operators that are legal, and I'll go into that in the next slide a little bit more. Basically, what can I do that's legal given an initial state? How can I transform that to another state, and hopefully a state that's closer to my goal? But how do I do that? The successor function is a way of applying operators in order to get those next set of states. The initial state and goal test. Again, I'm going to start off with some state I want, and I'm going to get something that I want to go to. That's kind of a satisfaction way. It gets a little bit different in optimization, especially when you have oversubscribed problems, because then you have to also choose what you want your final state to exist at. But we can talk about that later. Path cost function, which is how much whatever the metric I am using for determining what makes the best solution, path solution. This will be a way of measuring that, and we're going to use that as the metric for determining what's best. And as I said, there's lots of different examples. Okay, so let's go a little bit more into what a state. Here would be like an initial state, or any state that a puzzle would be in. Just from an implementation point of view, you're always going to have that decision of deciding about how to represent that state. So I just gave, for an example here, a 3x3 array. And you're going to have to figure out, it's obvious that you have some kind of on this array, and then for the empty space, you could put anything in here. I was just going to use 0, assuming that that's not part of the numbers. So that's how you start with a state. Then you're going to have operators. What are the legal transformations I can do on this that it will still, if I had a little plastic thing in my hand and I was going to move it around, what could I legally do given the constraints of that, right? So one of the, not interesting, but one of the neat little things here is that the way you think about this is, where can I move the space? Even though when you physically have the thing in your hand, you're always moving the tile. You think about, where can I move the space? Because that's just an easier way to represent it here. So if I can move the space to the left, I move the space to the right, move it up and move it down. Obviously, I couldn't move the space down here because I would be outside the dimensions of the game. So you're always going to check to see that they're, between dimensions are between 1 and 3, assuming that you're not 0-based in your array. So that would give this. I apply the successor function to this, right? I was able to move the 6 down. I was able to move the 7 over, and I was able to move the 5 over. So starting with this state, I can get to these 3 states directly by applying some subset of this operators. All right, and so if you then go recursively and go ahead and apply to each one of these, you're going to start building out a tree of all the possible states you can get to from this initial state. Okay. So what's a solution? And this actually, in games it's less interesting, but it gets more interesting when you're in real-world problems because you sometimes have to define what that solution is going to be. So a solution to a search problem is a sequence of operators that generate a path from the initial state to a goal state. So that means a path of operators that you're applying. So move left. So if I started you off with that initial state in that 8 puzzle, and I said, here I move left, I move right, move down, move up, you could go ahead and take the little plastic thing in your hand and move it around according to those directions, and you'd get to your goal state. All right, so it's just this path of applying those operators. An optimal solution is a minimal cost solution. So for example, we haven't talked about what we're talking about making optimal, but for that 8 puzzle, maybe it would be the fewest number of moves that you could do to get into that state, to get into the goal state. That might be an optimization, all right, as opposed to just satisfaction. And the solution cost versus the search cost, the key point here is that there's a cost for how long it takes, how many moves it might take you to move it to get to this goal state. But the search cost is how much time did it take you? How much memory did it take you to get that problem? I mean, it might have been that if you spent, you might have spent 5 days doing something, and you might have been better off just trying random selections of that. So this is always a critical factor, and you'll see it show up periodic, time and time again. Okay, choosing states and actions. So in games, again, because they're so well defined, it's not so hard to figure out what those states and actions are going to be. You're living in a very closed world with very precise definitions of what's going to happen. In the real world, it's often hard to figure out what are my states and what are my actions. What can I do? What do I care about? What don't I care about? So if I'm doing say I'm doing some kind of travel planning, and I'm talking about, I want to know if I can visit that city, that city, that city, and that city, and get back, and what's the shortest itinerary I can take to do that. Some kind of path planning. Do I care about the road conditions of the road? Maybe. If they're really lousy and it affects the speed I can go and the duration of those edges, then it matters. Do I care about the weather? I might. In access, the one with the paratransit of transporting the disabled and the elderly, one of the things that makes that problem tremendously complicated is that they really care about rush hour. So as you go in and out of traveling during rush hour, your durations become longer or shorter. So it becomes a much more complicated problem. If you don't have that problem, and you don't have to consider it, you would choose not to, and you'd use static durations between locations. So this kind of thing also shows up. I mean, initially, like when Google was doing path planning, when you ask how to get from there to there, they didn't care too much about duration shifts. But now that they're more integrated with traffic, they start to try to integrate. Given a certain set of traffic at this time, it would take this much time to get there. Whether you care about the names of the jobs or whether you just care about the functionality of the jobs, whether you care about looking at the color of the pieces. In a normal 8 piece, they're all the same color and you wouldn't care. But if you had to put together a picture that had you wanted to get all the blues in addition to the numbers together, suddenly those colors matter. So all I'm saying is that one of the challenges is always figuring out what are the states I'm going to need, and then what are the operators I can use to transform that. So one of the things that Niels Nielsen said in the early 70s is this is one of those famous quotes. I forget what the one that you said. That's effectively, what did you say? What was the one that you did?
That was Herb Simon knew.
Yeah.
20 years, it would be easy to solve all of them.
Right.
Easily have a machine of as smart as a human.
That's right. That's right. They passed the Turing test, essentially. So this is another one of those great statements where some pioneer in AI says that the problem of searching a graph has effectively been solved and is no longer of interest in AI researchers. And this is early 70s, and clearly it's an ongoing pursuit. So understanding that is pretty critical. That you can't really do. It's just, I don't even know how to respond to that now, because it's, there are, every conference you ever go to, you'll see additional ways to do search for different types of problems on graphs. Okay, so now we're going to start going into the sort of the aspects of search control strategies, and what are the dimensions you're going to consider when you're trying to figure out which search control strategy you're going to use. So one is order in which the search space is explored. If you have a big tree of things, you're trying to, do you want to just, some searches will just do left to right in that tree, or are you going to try to be very selective and try to minimize the search time? Are you looking for a particular value that will be optimized? You're trying to minimize the time traveled that you're doing if it was a traveling salesperson problem. To the extent in which partial solutions are kept and used to guide the search process, this is something you're going to be considered. If you're in a memory limited device, you're going to have to decide how much memory you're going to be able to expand. And even if you're not in the memory limited expanded device, it's amazing what exponential can do even with today's machinery. Exponential search strategies will eat up the machine very quickly, both in time and in space. So it's something always critical to understand is what is that space that you're going to be trying to implement. The degree to which the search process is guided by domain knowledge. Can you use sort of blind techniques, which we're going to be talking about today? Do you need to start adding very specific ones? You could start using heuristics, which we may talk about today, but we'll certainly talk in a later lecture. But more interestingly, you may even have very specific kinds of constraints and very specific kinds of ways, which makes the search highly tailored to that particular domain, which does happen, by the way, in the traffic. Okay. The degree to which control decisions are made dynamically at runtime. Some things you can do all in advance, as I was talking about with the access. Sometimes it's going to be a process where you don't have all the information up front, and it gets revealed to you as you're doing things, and you have to start changing it. Yes?
What exactly do you mean by partial solution?
Well, so you will have, I'll get to a little bit more, but I'll give you a little glimpse of the future, is this idea that you can have a partial solution that you can freeze at the moment because another one looks more attractive to you. And so then you start expanding out this other one, and then it turns out to be a dead end. You don't want to restart this solution, right? You like to be able to say, oh, I can go do something else. Or I can jump randomly to this to get over certain kinds of pitfalls that happen in search, which we'll talk about, which is like plateaus and those kinds of things. So it's this idea that you keep these solutions around so that you can then pick them up later on if the one that seemed more promising at the time doesn't pan out. Some properties that you would like to see in your search algorithms. One of them is completeness. Doesn't guarantee that you'll find a solution if one exists. All right. As we go through some of these these uninformed search mechanisms, you'll see where that doesn't play out all the time. So often what you have in kind of real-time event search is you throw your hands up at some point. You don't really care about whether it's complete or not because it's not going to happen in time. So you basically will look for so long and then you'll throw your hands up at it. Time complexity. This is what I was talking about before. How long does it take to find a solution? If it's going to be, on average, huge, you might be in problems. Usually, with good heuristics, you're looking to make this, in the worst case, is always going to be bad, but a good heuristic will often make it, on average, be much better and practical. Space complexity, again, how do you save all these solutions around? How much space do you need to expand this tree? that you're developing. And optimality. If you're concerned about optimality, is this thing always going to find the optimal solution? There's another concept that Herb Simon had, which was sufficing. And sufficing was this notion that it's basically good enough. Okay, satisficing, I'm sorry. It suffices and it's satisfactory, so it's satisficing. And often we'll replace this optimality with satisficing. It's a little squishier definition, but it's because the search spaces are very big in real world problems. Not always for the numerical, I agree. So now let's get into what a search tree looks like. It's going to be a graph of the search practices, implicit graphs and explicit graphs. It's going to be this notion of starting off with some search state, and in the case where we're doing generative search, we're going to start with the initial state, and then we're going to generate children, and then we're going to expand subsets of those children until we keep doing this by applying those operators until we find a goal state. How bushy the tree is, basically, is the branching factor. Like if I have a node that can have 5 children, it has that kind of branching factor. If I have a node that has 100 children, then the tree is going to grow much faster and be really branchy, and it's going to have a huge number of nodes. Generating and expanding states. What state is my state representation? How am I going to expand them? These open and closed lists, often the closed list is ignored, but it shouldn't be all the time. But what these are the open list would be the list of things that you still haven't solved, but you can return back to the state. And closed lists are the ones that you've expanded out and now you've put it in there so that if you ever come back around to it, like in a cycle, you can check against it. Also, you can update it too if you got there in a shorter path. And let's just go now to a sort of a detailed here. Let's suppose here's a generic node in a search tree. And it's just going to be, basically like a record. It's going to have some form of a state. So when we saw in the 8 puzzle, that would be that 3x3 array. It's going to have a parent node, which is just going to be a pointer to its parent. The operator is, what operator did I take? Did I move left, move right, move down to get down to that child, to generate that child? And the depth, what level of the expansion is this for that node? And the path cost to get down there. If it's in the case of the, suppose we were to minimize moves in the 8 puzzle, then that would be the path cost and the depth would be the same. But in the case where we're doing routing, you start to be concerned with the edge weights on those routes, and then the path cost is going to be dependent on those edge weights. Okay, so here's a really simple search tree. Again, similar to what we showed before. Here's when we're moving those spaces. This is when the 7 moved over, the 6 moved down, 5 moved left. And then we were expanding again down here. So the cost to get down here, if they were counting moves, this would be 1 move, this would be 2 moves. So all these are 2 move. Everybody see that from the path cost? This would be, this is the branching factor. There's 3 on each one of these things. Actually, the branching factor in the middle is 4. And these are the states. So each node would capture this information. This would simply be the state of that node, and all that information about depth and path cost would be also added for each one. All right. So now let's take a look at our first 5 different uninformed search strategy algorithms. So I've gone really broad, really breadth, hardly giving you any details, and now I'm going to give you details. Okay. So the idea of here is on a depth-first search, which I'm guessing a lot of you have already seen before, is that you're going to start off with some initial state. So when it says nodes here, the initial state will just be a list of one node, which is that initial state, and the state on that node will be, say, the initial board state, if we're doing the 8 puzzle. Goal P here is just some function for identifying the solution. So in this case, it would be, does the state equal 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8? A way of determining if you're at the goal state. And then a successors function here, and this is how do I, given a state, how do I generate the children state? the next level of steer. So, and this thing is going to return a solution, or it's just going to fail. The first case is going to say, if there are no nodes here, you failed. You couldn't find any solution. If you found a goal, if the first of the nodes is a goal state, beautiful, I'm there, I'm done. Okay, and I found that goal state. And what's going to happen is this is going to return a node, and remember that a node has a pointer back to the parent node. So if we walk that parent node back, we can get the path of moves, of operators, to get from that initial state to the goal. All right? This one? Oh, I'm sorry. Oh, I'm sorry. I'm sorry. This is too... my bias is I'm a list person, so that's why you'll see things like that. Assume that this is a list structure, and first is going to return the first element in that list. And rest down here is going to return everything in that list except for the first. Okay? So, and then if it's not a goal, we're going to do a recursive call here. And this is, understand that this kind of tree walking is inherently recursive. So you're going to see this recursive thing. If you're not going to do it this way, you're going to do it iteratively. Oh, yes? Successor means, in this case, what it means is the children. So if I start off with a state, it means all the boards I can generate legally by doing one move. I'm just using that as an example. So here what I would do is I would say I'm appending all the successors for the first one, and so I'm going to do them first before I do whatever in the back. So I'm always going to be doing something, if you'll notice, is that I'm always going to be walking down sort of what they usually say is kind of left-oriented. But I'll show you that in a second. And then we take the rest of the nodes and the goal being the successor, and we just recurse. Yes? Yes, yeah, absolutely, absolutely. Cycles, and it's really, this is one of the problems, is that if you have cycles or if you have repeated states, you'll have infinite, and there's ways that you're going to have to address that, and we'll get in, that's what we'll show in a couple of seconds. But straightforward, depth search has the absolutely massive risk that if you don't know your space, and you can get into cycles, it could not terminate. So here's an example of a kind of a simple road network, all right, where we start off with, we're in location A, and ultimately the goal is we want to get to I, all right? And so we can go here, these are the distances or durations it takes to go from A to B or A to C on these weights. And here's just here's the way the table is looked. And the reason I'm showing this is I'll show you how the recursion works. And again, here's just sort of transition tables, how you can get from A to the children, how you can get from B to its children. Now the reason I didn't put arrows on here and make this a directed graph is because I wanted to show the point that you already made, is that if you don't watch yourself, you could go like this, for example, and never get down to I, right? And going down a path. So what you want to do is, at a minimum here, I'm just going to do this for this case, just assume this, is the successor is never going to allow you to go back to the one that you came from. But that's not going to do very helpful in here, where you can get down to it by two different states. So assume from the moment that we're not going to address that issue, okay? So for here, because meaning that we won't be allowed transitions to go back. It'll be a directed graph. So given this thing here, what would you expect the depth first search to retrieve? What path? Given that it's represented that way. So it's kind of unfair. I'm not sure I gave you enough explanation. Go ahead.
If it's taking the cheapest successor to each point, we go A, B, D. Right, so you said a really key point here. You said the cheapest, right?
Depth first is blind to cheapest.
Okay.
So depth first is going to simply, because remember it did recursion, so it's going to do the leftmost. And if, that's why I have this kind of representation over here on this leftmost. So, but that's a good point. I mean, so leftmost would have been going down like this on the left side. So you'll see that. So, you know, A, B, D, G, I. And the path cost was 36. That's just adding up all these pieces. All right. So that gives you a sense of breadth first, but as you pointed out, it's got a big weakness. And as you pointed out, this is not optimal if we're looking for a minimum path. Right? Okay. So before we move on, let's just take a kind of quick look at sort of the complexity of this. What would you need? So if you let B be the branching factor and M be the maximum depth of the state space, then at any point, all you need is the deepest path, which would be M. So it's going to be the branching factor minus M is the space complexity. The time complexity is going to be the order of B to the M, which means all those states that you have to explore. Is this going to be complete? You know the answer to that? No. Yeah, right, but even then it's going to be hard to, you have to do cycle detection. Is it going to be optimal? No. Okay. All right, let's just go to breadth first now. Breadth first is very similar, but instead of looking at it through through Curson or through a stack, now we're going to look at it through a queue, or a FIFO queue in particular, first in, first out. So the only big difference is here. When we start to expand these, we're going to look at all the current level. So if we're here starting on a start initial node, make some children, rather than keep going down like that, we'll look at all these before you ever look at the next tier down. And we can do the same thing all the way through. And so that's the big difference here. All right? So again, back to our little example here. What would you expect to be the breadth first solution to find? Mishan? Yes, that's right. Does everybody see that? So the reason it's this is because, and again, it's with the weighted edges, it's suboptimal. This is not the shortest path, but it is the shortest number of steps to take to it. And so this is going to give you the shortest path because that's in that breadth. It found that before it could ever go to a more a solution that had more steps in it. Okay. So let's look at the complexity of this. D would be the level in which it found the solution. So the space complexity is that it would up to the point that it found that solution. Time complexity is again the order of the B to D because it's not going to ever go down below what it has to find the first solution. Is it complete? It is complete. Is it optimal? No, as we saw, it's not optimal. It would be optimal in what case? Yeah, so it's as long as the cost is a function of the depth, then it's going to be optimal. Good. All right, so now we have this problem is that we do have weights. You know, if we only had everything, if every transition only cost one, not a big deal. But now that we do have different weights to get from different places, how do we address that? How do we get that kind of solution? So this is the uniform cost search. And again, this is very much like breadth first search, except for what it does is it's, before it does anything, it's going to find the minimum cost node first. All right. So the first node is always going to be the minimum cost node in this case. So by doing that, you're always following just the minimum cost one. and that child will always be elevated first. All right? Okay. So now we're going to go here. Now I'm going to try to do one of those things. We'll see if I did it right or not. All right? All right, I'm going to try, so everybody can get their phones out, and hopefully I've done this right. Where is it? Is it? Okay. So now, I guess what I do is post this, right?
Oh, actually, sorry, you haven't posted it yet.
So I post it. If I said visible now, I didn't make it visible now.
You can make it visible now, then. Make it visible later, then we can check later to post it.
Okay, so I'll make it visible now?
Yeah.
Okay. And post it?
Yeah. Oh, but you also show names to us so we can tell who did it right. It's fine. This one might not count.
Okay.
You'll get test right.
Okay. Yeah, for me. So what else do I have to do here?
Oh, you did for the folder. And also make, so you have to check off the folder at the top.
Okay, I really made a mess.
I have it like in class.
Yeah, I saw that. So the problem is that my screen is now... Okay. So you made it here?
The in class folder.
I apologize for not having this... okay. Where's in class? Right here?
Yeah.
Okay.
And then go down, and then also select... After poll closes to show results.
After poll closes. After student votes, after poll closes, this?
Yeah.
Okay.
And show names to instructors but not students.
No names to instructors but not students. Okay. Now post. All right. Tell me if you can see it.
Yeah.
Okay, great. So let's just... Yeah.
It should be uniform costing, right now.
Yeah, I just suddenly realized that. Sorry. I suddenly realized that I was a little bit ahead of my game here, but that's right. You guys will be able to, this will work all right. Okay, so I was a little bit ahead of my game here. Where am I now? Okay, so for uniform cost, I'm just going to show you this because the question was for iterative deepening, so we're going to do it one more time. I just got too anxious about this. I'm so excited about doing this. So we'll see how this works. All right, so for uniform cost, let me just go on, then you guys will have a head start looking at the iterative deepening. For the uniform cost here, it's going to choose based on the minimum cost edge, which child to expand next. And as a result, you're actually going to get an optimal solution here, which is ACE HI, which has a weight of 26. So guaranteed to, let me just get rid of this. This is guaranteed to give you a minimum cost solution. All right. It has the same complexity as breadth first search, and that means that basically the depth it has to go to find the shortest solution is how much space it needs and how much time it will need. All right, now let me go. Okay, depth, I guess I have two more. Depth limited search. Depth limited search is very similar to depth first search, but it has a threshold. So what it says, and this is trying to address exactly, is that you say there's a limit to how far down you'll go. And if you get to that limit on the depth, you don't search any farther, and you backtrack, and you look at the other paths. All right? And obviously, you have to be very careful about how you choose that threshold. And is this going to be complete? No, not going to be complete. Is it going to be optimal? No. If you know it's not going to be complete, it's not going to be optimal. All right, so quickly here, this is a DLS. So here what you're going to do, if I set a depth limited search, and I'm using 4 as the depth that it will go to, this is the solution it would find, which would be A, B, D, I'm sorry, G, and I. So it doesn't, it's still doing left to right. It's not going to go, and it will find that solution. Okay? All right, now, Now, here we're talking about an iterative deepening search. So we do a repeated depth limited search, but what we do is we start off with like a depth of 1 or 2. And then we incrementally add the depth, and so we repeatedly do the search until we find a solution. Obviously, the disadvantage of this is that it's going to do redundant expansions. There are methods to address that, but it doesn't solve the problem. Is this complete and optimal? That's correct. That's right. Does everybody see that? He said complete but not optimal. And that's because it can find a path that will have fewer steps but more distance. And that would be a suboptimal path. All right? So now, now I'll answer your question. Yes?
You always start with the threshold of 1, or can you change the threshold?
You can, but assume for this 1. Oh. Yeah. No, I know. I just want to make sure. I knew you guys were going to be like that. I knew that was coming. It's like, can I see the tree? Okay, just give it a few minutes here.
Yeah, it has a vote. I have it up, so I know how many.
Yeah, I obviously can't go.
Right.
That's what I was trying to do, and I realized just as I was doing it, I'm like, that's not going to work.
I can just have mine up, and then I'll let you know.
Thanks. I appreciate it. I was talking to, in the past with instructors here, they would not be at the same time. They would, like ships in the night. So I appreciate it. Thank you. One of the key things to remember here is that it's expanding by 1 each level, each time it expands it out. And so think about what it will find first, given that assumption. That sounds good. What was the number now?
We're at 39, which is not everyone. So.
And I was so anxious, I jumped the gun. That's your final answer? Okay. Okay, let's see what we have here. See if I can find that.
So now go up top and click close the poll.
So close the poll.
And show poll results on the right.
Okay, and where are they? Down here? Aha! So, obviously I didn't do a great job explaining myself. I mean, this is great, but I'm still missing part of the class here, okay? So this is the answer. As I said, it's going to find, before it ever looks at the next level down, right? Before it ever looks at the next level down, if it finds a solution, it'll know if find a solution with more moves, if it can find one with fewer moves. So it's going to find this one with fewer moves, even though it has a higher cost in terms of the distance traveled. So that's the key part to remember here, because it's gradually moving the depth of that's searching the tree one at a time. So for those who voted this way, if you have questions about it, please ask me, please let me know. I'm assuming these people didn't just get lucky and that they actually know it and they understand it. So it means that I probably didn't explain it clearly enough. So if you have questions, please come and ask. I think either one of us can answer this question. Yep?
You got it correct, but does this and breadth always give the same result?
Well, this always gives the same result as breadth. I think it will. Let me just think for a second. I mean depth with a limit.
Oh, no, the breadth one.
Oh, the breadth one. Right. So it will, breadth will always find the shortest solution. Yeah.
So they'll be the same.
Yeah. So, but the advantage of this is that we're only expanding out in space as we need to. Okay. Yeah.
Well, what if there's two solutions in the same
Right. So it's going to find the first solution it finds in this particular way I have it set up. So if we're moving left to right on the.
Oh, it's not even looking at the weight.
Huh?
So even the inverted
No, because right now because it depends on how you define. We're not, like I said, there's no optimization here, right? It's saying is, can I get from A to B, or A to I in this case? And so it's not even looking at trying to minimize those weights here. Now, go ahead.
So in that case, breadth will give a different answer. If then two solutions in the same level, that would just return the first one whereas breadth.
Well, yeah. So if you look at, I mean, they're going to be kind of expanding. You know, I think that the depth one, right, is going to be kind of expanding like this, right, on a tree, like that, and the breadth is going to kind of go like that, but they're still moving left to right. So I think that if you found a solution, you know, if you found a solution in here, that's going to be the first one you find left to right. And I think the same thing here, it's going to be that same solution here. I haven't used a chalkboard in a long time. Anyhow. All right, well, great. Let's move on, I guess. Okay, so this is the example I gave you of this, and let me see if again, here's the solution. Okay, so now there's another type of search, which is this idea of doing sort of two searches at once. And it's a bidirectional search, and this is where you can start at the initial state and you can start at the goal state. And you can go back from the goal state, and you can go forward from the initial state. And each time you expand them, you can think of it either in parallel or alternating, like this, is that you compare to see on the frontier of this search whether the one that you've gotten to here, for example, is also here. And then you can combine those solutions. All right? This requires less space to do this, because as you get farther in the search going one direction, obviously the tree gets really wide at the bottom. So you're trying to get each tree a little bit smaller and just hit them there. So the time complexity, again, this is the path to the shortest solution, and you can divide it by 2 so that you never get down to those big bushy bottom ones. And same thing with the space complexity. High space complexity because the nodes have to be kept in memory to test for the intersection of the 2 frontiers. Okay, so these are all have these caveats now that we've all looked at them, so I just want to run through them just to make sure that we all have a sense of them and we understand this. So the time for the breadth first is going to be until it finds the shortest solution. The space is the same thing. Is it optimal? Yes, but in what situation? Only when we are as a function of the depth. If you have edges that have weights, all bets are off about that. Is it complete? Yes, it will always find a solution when one exists. Depth first. This is to the depth of until you run out of moves that you can do. So if you're in cycles, you're in hell. If your m is that depth of that space, so that's how much you need to be able to go all the way down there. The space, you only need to hold one path at a time. So it's this branching factor for the m. Is it optimal? No. Is it complete? No. Depth limited. L is the limit, the threshold that we're going to make it at. So that's what L stands for. So it'll either find a solution or it won't within that limit. The space is, again, that branching factor times that limit, because you're just going up and down. You're not keeping them all. Optimal? No. Complete? Yes, only if you can find that shortest solution before that threshold is hit. Right? But also if it's a function of the depth for optimality, as opposed to these weighted edges. Iterative deepening, again, you just have to go to the shortest solution, very much like depth, breadth first. I mean, space, same thing. Optimal, yes, in the case that you're not doing with the edges. And is it complete? Yes, it will find a solution. And the bidirectional, similar kinds of things here, small space concerns. Is it optimal? Yes. Is it complete? Yes. Yeah.
On the depth first, like if you never complete or you complete in some case, not always.
That's right. It's semi-decidable. So meaning by that, I didn't know what the background is. What that means is that yes, if it can find a solution on a path, but you remember, you could be, the solution might be, you could be here, and you could be going down like this, and the solution might be right here, right? But if you're going down like this, and this never stops, as she so rightly put, you're never going to get to that solution. Yeah?
If you use randomization, which is the trial you're going to focus on, would that in expectation?
Yes. So it would. So what they have is they actually have, there's actually a number of different methods to do this, which I wasn't going to go into too great depth. I was going to start it. But so some of the things they can do is you can do random restarts. So that's what if you look it up, you'll find that. So random restarts would be like, you stop here and then you jump, and then you keep going here. Other ones that they do are what are called like portfolio approaches. They do this mostly in planning. And portfolio approaches is you have a number of different searches that you're applying at the same time, and you try to do them conceptually concurrently. And so you will have jumps in here, and so you might have another solution that finds it here. The really good ones, and there are very few of these problems, they actually use one search routine to inform the other one about where to go to. But there are very, very few of that, and they're very precise about when they can be applied. So that's a great question. Okay, what time is it? Okay, go on a little bit. Okay, so I'm going to just start briefly into the informed search, but not go too far into it. So how do you improve the search? Well, you're going to want to avoid repeated states. avoiding repeated states is, this idea that you don't want to go into these cycles. You don't want to keep, if you have multiple ways to get there, you'd like to be able to say, oh, I've been there, I don't want to recompute it. And then expand it out yet again. Use domain knowledge to intelligently guide the search with heuristics. This is a key point. Everything I ever do always has some level of heuristics in it. Hey, is everybody familiar with the term heuristic? Okay. So it's usually going to be some domain information that's going to be applied in order to get to steer the search. And it's not going to guarantee that you're going to do better. And you may still end up expanding the entire search space, but on average, you're going to do better. All right, so for avoiding repeated states, do not regenerate states you just came from. So you keep some notion. This is the one that you don't return back. Do not create paths with cycles. Somehow you have to detect when cycles are going to happen, or you got to keep, one of the simplest way to do is you keep a visited node list, and you say, well, I've been there. And the only thing you care about at that point is if you've been there already. If I got there in a shorter path than I got there before, then I need to update anything in which that was the path and I expanded out from, and update that cost all the way down. Do not generate any state that was generated before using a hash table to store that. So this is just a way of implementing that kind of visited node list. Okay. So what are heuristics? Heuristics are problem-specific knowledge that reduces expected search effort. We'll show you how to use them in terms of some of our search routines and helping to decide which of the children you're going, next of the open nodes that you're going to expand and then search. The heuristic functions evaluate the relative desirability of expanding the node. As I said, you're going to be presented with a set of open nodes that you haven't searched as you go through and generate your tree, and it's always a decision of what's the next one I'm going to expand. Which one am I going to look at? Heuristics often estimate the distance to a goal, so that's a really easy way to see it. It doesn't always work that way. It makes it harder. Coming up with good heuristics for domains is not always easy. It's not always easy to find a good domain. But for the example, the one where we're doing distances, if you say, oh, like I'm traveling, if I can say what's the distance to that goal, that's a pretty easy one to realize. There is such a thing as called admissibility, and we'll talk about that. And basically what that says is you got to be really careful, because even if it seems obvious what that heuristic should be, you never want one that's going to overestimate the distance to the goal. In blind search techniques such as knowledge can be encoded only via state space and operator representation, right? We really can't see sort of a larger scale of things. And so we'll start, when we start talking about how to form heuristics, we'll start seeing what the kind of things we're going to try to consider. Okay, so some examples for heuristics. Travel planning is Euclidean distance, right? So one way you could do that without ever overestimating is that if you had I was at location A and I have all those other locations out there, but I didn't really know the road network, for example, I could just say, give me the Euclidean distance from my spot to a straight line, right? And that's going to give me an underestimation of the distance to actually go there. But that'll give you a heuristic of one way to do that. So you pick the next one you pick would be the one that would give you the shortest distance there. For the A puzzle, there's actually a couple ones with Manhattan distance usually performing better. And that's that if you imagine in the A puzzle, you have this state, whatever state it is, and you have a goal state. One way is just to count the number of tiles that are not in the right place, right? And that would be, that's the value for that. The other way to do it would be to pick the one that says Manhattan distance, which says, given all the tiles, Manhattan distance being like block travels, so it always has to be in straight lines. You count how many away you are, and you just sum up all the ones, and that will give you the count for that board, the distance from the solution that you are. All right, so obviously, if everybody's in the right place, it's going to be 0. And so that's a way, you can imagine generating a bunch of children, looking and saying, oh, that one has the shortest distance to the solution. So I'm going to expand that guy, most promising one. So I forget who it said, but someone says, oh, you're not even considering distance. But so you might try to pick the one you think is the shortest distance from there. It may not work out because if you're using Euclidean distance, for example, and your network didn't support Euclidean distance, and you had to take some circuitous route rather than some direct line, then that's going to lead you astray a little bit. Yeah. Right. So I'm just, if you're like advancing, you saw my slides, right? So their monotonicity is absolutely a critical factor on these heuristic values. Is that whatever you do, that's why you don't want to you never want to be able to go to something that it's ever going to decrease in its solution. Okay. I'm not sure. I mean, if I think about travel, I think about it. If I think about travel, right? If I'm on a particular path, it's never going to get less. Right? It's never. I mean, I've gone that far. I am where I am, basically, right? It's never going to get less at that. So I think in a lot of real-world domains, you do get some of that monotonicity. What you don't get is the monotonicity on the frontier. Is that you'll jump from here to this part of the search to here because now this one appears shorter because I took a really long. I went to Anchorage, Alaska, and I didn't realize that, in order to get there, and I shouldn't have gone there. And so now it's better to jump over here in this state. There's an algorithm for computing the minimum spanning tree for a traveling salesperson, and this is something that allows you, again, to select which city you're going to visit next as you're doing the search. I forget what the name of that algorithm is. Kalman? I can't remember what it is. Anyhow, there's an algorithm for doing that. It's a closed form solution for generating a minimum spanning tree from that solution. But that doesn't give you the solution to the traveling salesperson problem. It just gives you that spanning tree. So heuristics from relaxed models. Heuristics can be generated via simplified models of the problem. Typically what I said is designing heuristics for real-world problems can be kind of difficult. And so often what you will do is you will try to simplify the problem and then try to use that simplified version of the problem to design your heuristic. Simplifying the problem, when you say relaxed, one of the notions is this idea of relaxing constraints. So for example, in scheduling, you might say, yeah, there really are due dates, but I'm just going to ignore them. It's all right to have things come late. And so then I can start simplifying based on allowing for due dates, allowing for things to push late. All right. This is something that I don't know how many papers I read in conferences that people just, it's like a fundamental thing, but people just don't pay attention to. And they come up with these great heuristics, but the complexity of figuring out the heuristic is more complicated than the search itself. So it's something. I mean, it seems trivial, but be aware that you're running these heuristics every time you generate every one of these children. You're calculating on each one of these nodes. So if it's inefficient in itself to compute that heuristics, like, oh, I'm going to measure it all the way back and figure out that, then you're lost your purpose while you're doing it. Okay. Okay, so I think that it would be better if I stopped here and then we'll go into, we're starting the structure of heuristic search. And so when we come back in, unfortunately, or actually fortunately for you guys, you'll have 2 great lectures from Zico and then you have me after that. All right, thanks a lot.